I'll do it again. Good evening, everyone, and welcome to the next seminar of the Center of Institutional Studies at the HEC University. Our speaker tonight is Mikhail Drugov from the New Economic School. Mikhail is a professor at NES. His PhD is from the University of Toulouse, and his masters are from NES and actually HEC. He does economics of information, industrial organization. He does experiments and lately contests. And tonight his talk is going to be about contest successful, about hunting for the discouragement effect in contests. So, Mikhail, the floor is yours, and I would like to remind everyone to please identify yourself in the chat column of this presentation. Thanks.
Okay, Leonid, thank you very much for introduction. It's a pleasure to be here. I should add that actually my bachelor's degree is also from HEC, which is 4 years, right, versus 2 years for the master's degree. So I think this is even more important. So anyway, so I'm happy to be here, and thank you very much for coming. So this is a joint work with Dmitry Rivkin, who is my kind of regular co-author on contest papers, who is at Florida State in Tallahassee in the US. And yeah, the title you see, Hunting for the Discouragement Effect in Contests. So I should say this is really the first time, well, the first and a half, second time I present this paper. So I will try best to do that it's clear. And so please, of course, ask questions if something is not clear. And okay, let me start. So what is a contest? So this is a situation where several players invest their resources or efforts to win a certain prize. And the key feature of this situation is that the resources are sunk, so they are kind of lost, even for those players who don't win the prize. Okay, so this is like all pay. So everybody spends, but of course, in the cases you have several prizes, several people win, but those who lose still, don't get back their investments. And so this is a very, very common situation. So contest or tournaments, so that's like synonyms for me, and in the stock, they're everywhere. So here are a few situations. If you think about bonuses and promotions in the workplace, not everybody can be promoted. You work hard to win a promotion, and whether you're promoted or not, still your hard work, is done. Think about R&D races. So firms invest to do, to be the first, to be the best. So here you can say that maybe the price depends a bit on your investment. So in each situation, there are some variations on this basic model, but the idea is the same, right? So not everyone wins, but even for not winners, the resources are spent. Think about sports, which are of course designed as contests. Think about elections, right? Only one wins. Think about trend seeking and lobbying. That's actually was the original motivation of one of the sort of seminal books in this literature by Talok. So actually on the right, you have Elon Musk, the second richest person in the world since recently. So anyway, these are their lobbying expenditures for launching the US military satellites about 10 years ago, okay? Then you can think about litigation. You have the prosecution, you have the defense, and it will be guilty or not guilty, right? So this is again kind of a contest situation. And think about a conflict or a war. Okay, so the sides invest into their military spending, into their armies, and yet, of course, maybe there will be only one winner. So there are many situations. So these are very important and kind of common situations. And there is a common wisdom in the contest literature is that heterogeneity is bad for effort. So when players are different, then their total effort, so total resources. So here, I will be using effort for resources or investment which are spent in the contest. So if players are different, total efforts are going down. So here's a quote from a recent survey by Fu and Wu. So Fu is one of the sort of very active researchers in this field. So that's a survey. So they write what is well known, and it is well known in the literature that the performance of a contest crucially depends on the competitive balance among contenders, and the more level playing field tends to full competition. Okay, so competitive balance or level playing field, these are all these sort of, if you want, synonyms for homogeneity, right? So how close you are means you have a higher competitive balance, and the standard advice to level the playing field, right? So to put the players on equal footing. Why? Because it fuels competition, it strengthens competition, and total efforts go up. So total effort is something that you care about by assumption, right? So in a contest, in a real life contest, you can care about many things. So the literature typically looks at total effort. Of course, that's not the only assumption, not the only possibility, but that's the most common case. And we'll be here as well looking at the total effort. Here is another quote which describes the mechanism, or one of the possible mechanisms of why this happens. So why heterogeneity is bad for efforts. So it says the theoretical literature on contests has recognized that greater heterogeneity between players leads to lower aggregate effort. The reason for this is the so-called discouragement effect. Also, the technical details underlying the discouragement effect differ from model to model. They basically arise because a weaker player finds it relatively unprofitable to try to beat the stronger player and consequently cuts back on his costly expenditure. This in turn may allow the stronger player to bid more passively when compared to a contest in which he faces a player of a similar strength, right? So in other words, the weak player, it's too difficult to beat the other one, so he reduces his effort, and the stronger player replies by also reducing the effort. Okay, so this is a possible mechanism, and again, this is a quote from a survey, and actually Kovinok is also kind of a top figure in this literature. So these are not some marginal papers, not marginal people. This is really a common wisdom. And so as an example of such a situation, consider this contest. Okay, so this is based on Talak contest. So Talak is probably the most famous kind of person or reference in this field. So this is a probability. So the key object is the probability that one player wins given all the efforts. And so it depends not only on efforts, but also on types. Okay, and so the key object is this probability of winning depending on the efforts of two players. So we consider the case of two players. I can tell you later what happens if you have many players. Here are two players. And so it's almost standard Talak form, but just each type kind of multiplies your effort. Okay, so it makes the effort kind of more efficient, more effective, if you want. Okay, suppose the linear cost of effort, and you solve this this model, okay, and you find that the total effort is a function of a ratio of the two types. Okay, and well, I don't know how clear it is, but the point is that as this ratio becomes further from one, so when it's equal to one, it means that there is no heterogeneity because the two players are the same. So as this ratio becomes further from one, total effort goes down. And that's kind of the standard case, which is discussed in the literature. Okay, so this is just an example. But consider an example which is based on the Lazy-Rosen model. So this is another classic reference in this literature. So they wrote where they introduced tournaments. A tournament for them, well, it's basically a contest. It just, they call it tournament. So the output of a player is his effort plus some random shock. Okay, how lucky he is and what happened. And for simplicity, it's additive. And the cost of effort is quadratic, again, something simple. And suppose that the difference between the shocks is uniform on some interval, actually, doesn't really matter where. And suppose that the type multiplies the kind of makes the effort more effective multiplicatively as before, but it also kind of hurts proportionally the other player. In other words, the probability of winning is given by this expression, and you see that your effort multiplies your effort and it kind of hurts the other player. And the same for the, so your type, right? And the same for the type of the other player, and it's additive because of the uniform distribution, which is just for simplicity. Okay. Now you solve this model, just take two first order conditions, and you obtain that in the equilibrium, the total effort is given by this function. And you see that this is the ratio of types plus the inverse ratio of types. And this function looks like that if you increase this ratio, actually the total effort will go up, not down. It will go up. It's minimized at equal types. So it's the complete opposite of the previous examples, of the previous example. And so our questions here are really very simple. What is wrong or what is right with this example? Can it be generalized? And also, when we say heterogeneity is bad for effort, so what does really mean to be more heterogeneous? Right? So if you think about it, it's not entirely obvious if you know these two types are more different in one way or the other than some other two types. And what we show is the following, is that there's nothing wrong with this example. There is nothing wrong with the first example either. This is just that there are different models. And so we classify many, if not most, existing contest models into two groups. So actually the literature doesn't use too many different models. And basically we cover most of them. And so in the model of the first group, there is either discouragement effect, as it was in the first example, or there may be the opposite, which is encouragement effect, as was the case in the second example. What it means to be heterogeneous in the model of this group, it's kind of very big notion, I will explain you. And it's related to the biased contests. So this is another sort of related common wisdom in the literature, which was saying, look, that the bias is bad for efforts, right? So if you take, say, identical players and then you favor one of them, this would be bad for total effort. You see, so it's very similar. And actually, so we have a previous paper which argues that, look, again, there is nothing general in this wisdom, and we'll provide some results about that. But essentially, the discouragement effect in kind of this model is very similar to when the optimal contest is unbiased, right? And if you think in terms of applications, that of course is crucial, right? So you want to fight, you know, patronage and favoritism, etc. And the question is, what are the theoretical underpinnings of that? And actually, I should say, so this is all grew of kind of a paper that I presented in this seminar, I think 2 years ago, on patronage. And so there, I got interested in a question, when is biased contest bad? And the literature was saying, well, always, and I clearly saw that this was not the case. So anyway, so we have a previous paper when we look at biased contest, and a biased contest, it's some particular way to introduce heterogeneity. So here you can see that we introduce heterogeneity in a more general way. Now, in the model of the second group, actually how heterogeneity is introduced is crucial for where there is discouragement or encouragement effect. Because if you say, look, they become more heterogeneous, you need to say how they become, in which sense, and depending how you define it, you can have encouragement or discouragement effect. So I haven't shown you an example of this sort, and of course, when the time comes, I will show you. Okay. So,
sir, may I ask a question?
Sure.
I just didn't get whether we ask on the go or after the seminar, but I hope it's okay. But actually, Do you have any empirical support for this story? Because as far as I know, most empirical studies indeed find the discouragement effect. And I'm not aware of any studies which actually don't.
Look, that's a very good question. And that's, so we don't really want to overturn. So this will be my conclusion. We don't want to overturn the, you know, all the policies that are aimed at making people or players more equal. We're just saying that the evidence for why this policy should be employed should not be coming from the theory. The theory doesn't give you an unambiguous answer. The theory is ambiguous. And so this is our way to kind of structure a bit the existing theory and to say, look, in which cases you get it and in which you don't get it. Okay, I totally agree with you that in reality, probably the most common case is that heterogeneity is indeed bad for efforts. Whether it comes from this model, and this is the right model, I don't know. Maybe there are some psychological effects involved, which of course the standard theory doesn't model. So, but it shouldn't be, the claim shouldn't be based that the theory shows that this is like this, because this is not correct.
And one more quick question. So basically the specification, like the second specification you showed to us, for me it reminds a bit the model of contest with sabotage, where the effort you may exert is actually two-dimensional. You have a standard productive dimension and you have second dimension, which is probably unproductive and which we usually call sabotage. And it would be nice to see that maybe there is some way to construct a mapping between these two approaches you showed us as the second one and the model where we have a contest with sabotage activities. Because the fact that my effort cost affects my opponent negatively looks a bit like a sabotage.
But look, so in a contest, because it boils down to relative performance, right? Either explicitly as in Lazy-Rosen or implicitly as Untitled, any effort which is good for me is bad. Any type which kind of improves me, it's bad for my opponent by construction because it's all relative. Okay, so, and look, so I'm now at the slide of the model. So you'll see that kind of we have a general formulation that, yeah, in some cases, I agree with you that types can be conceived as sort of harming your opponent rather than sort of improving your performance. So,
well, might be a good idea to remind that the price is fixed. So anything that improves you makes the other side worse off. So yeah, it's hard to distinguish between productive efforts and sabotage, because none of these are actually productive. All of this is rent-seeking, quote unquote. Yeah. You do not create value. Okay. Thanks.
Okay. So the model is two players, and the players one utility is given by this function f, which depends on both efforts and both types. So the effort of the second player, of the other player, is always bad for you. Your type is good for you, and the type of the other player maybe is bad for you, or maybe it has no effect directly. Okay, so maybe the type of the other player affects, for example, the cost of the other player, and hence it doesn't affect you directly. Of course, in the equilibrium, it will have an effect on your utility, but there is no direct effect. So in contest, usually this function f consists of three parts: the valuation of the price, which may depend on your type. This is what is called contest success function, the probability that player one wins, given efforts and types. And then minus the cost function, which again may depend on the type of the player. Okay, so this is the model. Now, the game is symmetric. So if in this function f, you swap the efforts, you see now it's E2, E1, and you swap the types, you get the utility of the second player. Now, we need to impose some regularity conditions that, you know, these utility functions are concave, and first of the conditions give you indeed the optimum for each player. So this is pretty standard and simple. So once you have it, then we have the equilibrium, which is characterized by two first order conditions. So each player optimally chooses his effort. Okay, and here they are, the condition for player 1 and a similar or symmetric condition for player 2. You solve it, and you get the total equilibrium effort, E star, which is the function of the types, T1, T2, which is of course just the sum of the two equilibrium efforts of the two players. Okay, and so our interest is how this object, capital E star, depends on T1, T2, but in particular in some notion of heterogeneity, some notion of difference, of, yes, difference between T1 and T2. So let me introduce these two groups or classes of models that I mentioned before. So we'll be calling them models with relative types and models with absolute types. So a model with relative types is a model in which the total equilibrium effort E star does not depend on the types if the types are equal to each other, right? So if the types, as in the examples before, you remember in the both examples, what mattered for the total effort was only the ratio of the two types. So if the two types are equal to 5 or both are equal to 10, there is no difference. And in this case, we call this model a model with relative types. Otherwise, it will be absolute types. Okay. Now, so consider first models with relative types. So how do we introduce heterogeneity? We just make one player stronger, or maybe one, the strong player stronger, and or the weak player weaker. And in this case, we say that the types become surely more heterogeneous. Why surely? Because it's a very weak definition. If you want that kind of, it's sort of obvious. If you want obviously more heterogeneous, and here's the picture, right? So you have the space of T1 on the horizontal axis, T2 on the vertical axis, you have diagonal, right? On the diagonal, the two types are equal to each other. And take some types, you see this black dot. Okay, so here T2, right, so is stronger than T1. So here the second player is stronger than the first player. So what does it mean to become surely more heterogeneous? You need to go up or left, right? So you need to either increase this type or decrease the other type, right? So, and this gray area shows you those types which are surely more heterogeneous than this initial type, the black dot. So because it's all symmetric, you can also have the same, right? Because it will be all symmetric. So if you take a type, right, which is the opposite, just reflected about the diagonal, again, you have this second gray area, which is surely more heterogeneous types relative already to this point. Okay, so this is a definition, and you see it's very weak. And you see that for absolute types, we'll need a stronger definition, and it will be more nuanced. But for relative, this is as weak as this. Now, here comes a big assumption. Let me tell you, and then tell you why it's big and why it's not big. So suppose that the first derivative of the utility function of each player, this, can be written as some function of the two types. So the two types, T1, T2, enter this first derivative only through function tau. They don't enter independently, they enter only through this function tau. And because your type helps you, the derivative of tau with respect to T1 is positive, and the other derivative is negative. So why is it a big assumption? Well, because of course, that's a super particular functional kind of restriction on the functional forms. Why it's not a big assumption? Because basically all the models with relative types that we are aware have this form. Okay, so our claim is not kind of to provide a general theory of everything that can happen. It's rather to provide some kind of classification or systematization of those models which are used, which are popular in the literature. And so to our knowledge, basically all common models with relative types, they have this structure. Now, because we say that when you have relative types, the types don't matter if they are equal to each other. It means that this function tau is constant for any types, right? So for any TT, so for any types when they're equal to each other. And then we can rewrite the total effort as a function, some function phi of this function tau of the types. And here comes the first proposition, which is very simple. It's just an observation. And it's, of course, super simple. And let me just draw it. So we're saying, suppose this function phi is unimodal and maximized at tau bar. Well, then, as types become more surely heterogeneous, the total effort goes down. Well, that's obvious because, of course, as types become more heterogeneous in this sure way, you go either here or here. And if the function phi looks like this, of course, total effort goes down. That's as simple as that. And the opposite case is, well, the opposite. So you have this function phi, which is minimized at tau bar. Okay. And in this case, instead of discouragement effect, you have encouragement effect. And that's precisely what we had in our examples before. In the taluk example before, you remember, this was the shape of the total effort. So this function tau is the ratio of types, and the function phi is this function, and it's unimodal and maximized at tau 1 equal to 1. So when the two types are equal to each other. And then the total effort decreases with heterogeneity. In the second example, it was the opposite. So tau again is the ratio of types, but now phi is tau plus 1 over tau, and it's U-shaped. It's minimized at equal types. And so now you have encouragement effect that the total effort increases with heterogeneity. So look, we really here didn't prove anything. It's just an observation that basically all the models in the literature with relative types, they have the structure. And so sometimes, or maybe in the most popular models, you have discouragement effect because this function phi happens to be unimodal. But it's very easy to construct other models which are sort of look reasonable. There is nothing really weird or complicated where you have exactly the opposite. Okay. So this is this is really just classification. Now, if there are no questions, let me move to absolute types. Okay. So what happens with absolute types? And first, an example, right? So types are absolute when the total effort, when the types are equal to each other, depend on to what they're equal. So take the most standard taluk contest with heterogeneous players. The probability to win depends only on the efforts, on the relative efforts. Leonid, you have a question?
No, I'm fine. Yes, okay. Sorry about that.
And the types is the marginal, or rather inverse marginal cost, right? So a higher type means that you have lower marginal cost. And in this case, the total effort has this form. And of course, you see that if the two efforts, if the two types are equal to each other, still, of course, total effort depends on what they equal. Well, obviously, because types decrease marginal cost. So if both types are high, marginal costs are low, there is a lot of effort. Both types are low, marginal costs are high. And of course, the effort is low. So obviously, so that's again, right? So this is the most common really taluk contest with heterogeneous players. Now, note that the total effort in this case was equal to the half of the harmonic mean of T1 and T2, right? So what is the harmonic mean? Well, this is some kind of average of two numbers, or maybe more than two numbers, but here we have just two numbers. And this is actually a general point. But before I move there, let me introduce what does it mean for some function of T2 numbers to be their generalized mean, as it's called. Okay. So a function m is a generalized mean of T1 and T2 if it's monotonic in both arguments, right? So you want that, say, the easiest way to think is, of course, that it's increasing in both arguments. Second, that it's symmetric. If you change the order of the two numbers, the average shouldn't change. And finally, if the two numbers are equal to each other, this function, kind of their average, should be equal to the same number. So that's it. Right? So any function which satisfies these three properties is or can be perceived as a generalized mean. Right? So it's sum average or mean, and it's generalized because, of course, it's not arithmetic, it's harmonic, it's something more general. And now let me provide the first result here, is that in a model of absolute types, there is always a unique generalized mean such that the total equilibrium effort is equal to the total equilibrium effort when both types are replaced by their generalized mean. Okay, so in other words, take any two types, replace by their generalized mean, and the total effort stays the same. Okay, and so the proposition says that for any model with absolute types, you can always find such a generalized mean, and it will be unique. Okay. So in other words, you can always homogenize the type, right? So replacing by their generalized mean, it means you homogenize them, you make them the same, right, at some level, and the total effort will not change. Okay, and we say in this case that this model is characterized by this generalized mean M, which of course immediately implies that how you introduce heterogeneity depends on how this heterogeneity compares relative to the generalized mean characterizing the model. Okay, so in other words, you can introduce heterogeneity in different ways, and on the next slide you will have a definition of how you can introduce heterogeneity. But whether it will increase the effort or decrease the effort will depend on how that notion of heterogeneity compares to the sort of this notion, which is generalized mean. Okay, and so it will be more clear, there will be pictures on the next slide. So, definition. So we introduce a notion of more M heterogeneous. So two types, T1 hat and T2 hat, are more M heterogeneous than T1, T2 if, first, it's surely more heterogeneous, and second, they have the same M mean. So in other words, you want to make them surely more heterogeneous, so you want to make stronger type stronger and the weaker type weaker, but you keep this generalized average constant. So on the picture, so remember our picture we had before, so you have, say, this point, right? So you have the point here. Okay, so the gray area is surely more heterogeneous than this point. And then you draw, for example, a constant arithmetic mean, right? So the sum of the two types is constant. And so more heterogeneous, so as you move by black arrows from these corners, you get more heterogeneous in the sense of arithmetic mean, right? So you keep the arithmetic mean constant and you make the points, the types, more surely heterogeneous. And so you get more heterogeneous in this arithmetic mean sort of sense. Now, you can take, of course, constant harmonic mean, right? And you can make more heterogeneous in the sense of this mean by moving along the black arrows on the kind of on the blue line. Okay, so again, so this is a kind of finer definition of higher heterogeneity, right? So you need to be surely more heterogeneous, but you also need to keep some particular M mean constant. Now, and to see how it works, so suppose kind of say the case we had before in the Taluk example, that the direct effect of each type is to decrease marginal cost, which will lead to the increase of the effort of the player, other things being equal. And so then as you introduce heterogeneity in this way, so the stronger player becomes stronger, he increases the effort. The weaker player becomes weaker, so his costs are higher, he decreases the effort. But the total effect is ambiguous, right? Because one goes up, the other one goes down. And this is only direct effects. And there are, of course, indirect effects because the optimal effort of each player depends on the effort of the other player. And so there are indirect equilibrium effects, which are ambiguous too, in general. And so that's why kind of, in general, it's ambiguous what will happen. But what is clear is that the magnitudes of type changes matter. That is, in which particular mean or sense you introduce heterogeneity is crucial. So let me come back to the picture. You see, if you go along the arithmetic mean curve, you trade the two types 1-to-1, right? So
I think you're breaking up. You're breaking up. I'm not sure if it's, yeah.
You mean my connection?
Yeah, well, oh my, I'm not sure, but Bernardo, is everything is okay on your side?
At least I can hear everything perfectly.
All right, I'm sorry then, it might be my problem, so please go on. Sorry about this.
Okay, so if you move along the arithmetic curve, average constant, then it means you trade the types 1-to-1. The stronger type becomes stronger exactly kind of by the same amount as the weaker type becomes weaker. But if you go by the harmonic mean, then actually by this black arrow here, right, then it means that the stronger type becomes much more stronger relative to how much weaker becomes the, right? So you see the change here is this, and the change here is that, right? So the kind of the trade-off is very different. Qualitatively is the same, but quantitatively, of course, it matters a lot along which curve you are moving. And this brings us to the main result in the absolute type case. But before I introduce it, let me parameterize these generalized means. Okay, so we consider a family of means which are parameterized by a parameter rho, and the means are increasing in this parameter. Okay, and so the most famous family which is used, this is power means, which have this form, and doesn't really matter what the form is. The important thing is that the three most used averages actually belong to this family. So arithmetic mean is as a part of this family when rho is 1. Harmonic mean, it means rho minus 1. And geometric mean is between is m0. And we know that among these three means, arithmetic mean is always the highest and harmonic mean is always the lowest. Okay. And so this brings us to the main result in the absolute type case is this proposition. So suppose you have a contest model which is characterized by generalized mean M with parameter rho 0, okay, belonging to this family with parameter rho. Suppose that this family has the Spence-Mirrlees property. Actually, Leonid, you taught me that 20 years ago, Spence-Mirrlees property in Micro 4.
It hasn't changed much since that time, so that's fine. It's been fairly stable.
So the ratio of the partial derivative is increasing in rho. So I will show you what it means. And then if you introduce a higher M heterogeneity with parameter rho, whether it increases or decreases the aggregate equilibrium effort depends on how this rho that you introduced, right, compares to the rho 0 characterizing the model. Okay, so now let me explain you what about this Spence-Mirrlees property. So this Spence-Mirrlees property, or in other words, single crossing property, ensures that these two means, right, of rho 0 and with rho cross at most once. And moreover, the distance between them grows from the intersection point. So this is the best to be seen in the picture. So let me compare to this picture. So you see here, right? So if you take the crossing of the arithmetic mean and harmonic mean, oops, okay, right? So you take the crossing, and as you move, right? So say here somewhere, right? The distance between the two increases, right? So these two means have this property, the Spence-Mirrlees property. So if you have this family which has this property, then you have this result, okay? Is that if you introduce M heterogeneity with rho, which is higher than rho 0 characterizing the model, total effort goes down. If you do the opposite, so rho is below rho 0, then actually total effort goes up. Okay, and let me just show this on the picture. And so the picture is here. So let us take our example. Okay, so our example, you remember total effort was half of the harmonic mean. And let us bring our picture. So this is the picture we had before. The gray areas, right, are surely more heterogeneous, right? So this is the blue line is a line of constant total effort in this example, right? So the constant harmonic mean. Introduce now higher heterogeneity in the sense of our constant arithmetic mean, okay, which is this red dashed curve. Okay, and then as you move kind of to more unequal points, to more heterogeneous, total effort goes down. And that's kind of the standard, that's what the literature is talking about. But why should you introduce heterogeneity in a way that keeps the arithmetic average fixed? Why arithmetic? I mean, of course, arithmetic average is very simple and popular, but yet it's not the only one. What if you introduce heterogeneity in this way? So what does this mean? Well, it's some other mean belonging to the family of power means. Yeah, it's maybe less popular, but it's some other mean. And if you introduce heterogeneity, right, in this sense, the total effort will go up, right? So as you move from these points along the black arrows, right? So that's a higher heterogeneity in the sense of this mean, which is actually, so this is m minus 2 from the power family, and harmonic is m minus 1. So total effort goes up, okay? So that's the notion of, you know, how introduce heterogeneity is crucial for knowing its effect relative to the model where you do it. And let me finish with the simple corollary for the power mean family. So the power mean family, as I told you, has this Spence-Mirrlees property, right? So I showed you for, well, you saw it 3 different means from this family. They clearly have it. It's true for any means from this family. Moreover, in this family, this parameter rho is unbounded, right? So it doesn't have a maximum value you should take or the minimum, which means that if you have a model which is characterized by some mean from this family, you can always find heterogeneity in the sense of kind of rho prime and mean or rho double prime and mean, such that in the first case, total effort will go down, and in the second case, total effort will go up. Right, so it's always possible to introduce heterogeneity in a way that increases or decreases the total effort. Right, so all the conclusions about the robustness of whatever encouragement or discouragement effect are really up to, you know, the question how you introduce heterogeneity relative to the model that you are studying. And so let me conclude. So what we did in this paper, we classified, or we, if you want, introduced a classification of many popular contest models used in the literature in 2 classes, relative types and absolute types. When the types are relative, it doesn't matter how you introduce heterogeneity, you either have always discouragement effect or encouragement. Maybe models with discouragement effect are slightly kind of more known, or a lot more known, but there is really nothing fundamental why you should observe the discouragement effect. And when the types are absolute, it all depends, as I just said, I think 5 times, on how or which heterogeneity you introduce. Okay, in other words, in any model, you will have both discouragement effect and encouragement effect. Now, let me say so what Nastya asked before, more or less. So we don't say that, of course, in real world, you should now kind of change something. It's rather that the theory is ambiguous, right? So the theory doesn't support kind of exclusively the notion of the discouragement effect. This is up to the model. And also, it has implications for dynamic contests. So in dynamic contests, there is such a thing as called momentum effect or dynamic discouragement effect. So this is the case when you have early victories, right? So you have symmetric players in the beginning. Somebody wins the first stage, right? And it creates asymmetry between the two players. And then this asymmetry reduces total effort at later stages. And this is the standard momentum effect. But our results imply that maybe actually you'll have sort of anti-momentum effect, right? So that is again, the theory is not that unambiguous as presented often in the literature. And that's all. Thank you very much.
I like your concluding slide. Okay, please, questions, answers. Any comments? While people are thinking about what to ask Mikhail.
I have several questions, but I don't want to take a lot of time actually, if other people also have questions.
All right, so go ahead and we'll see how much time it takes, because I have a couple of questions as well.
Yeah, so that's a very interesting mechanism and a very nice characterization of a pretty general setup of contest models. So my first question is, does it also apply to all pay auctions where the noise is basically zero?
Yes, that's a good question. And the true answer, I don't know, because, you know, kind of, as you know, people in the literature work usually either with all pay auctions or with kind of noisy auctions. And I don't know about all pay auctions. It's a good question. It's a fair question. And I cannot tell you now.
Okay, fair enough. The next one, please.
So can I still ask?
Oh, absolutely. Yes, right. We're waiting for your next question.
Okay. Then basically your results do not depend on the specific noise distribution, right? It's just about specification of the cost function.
For relative types or absolute types?
Like both.
Okay, well, not really. So if you look at the very first, well, the only Lazier Rosen example that I showed you, right, which is here, of course, the contest assess function, which is this, depends on the noise distribution. So you have this plus and minus only because the difference is uniform. If you have, I don't know, normal noises, then you have something quite different.
No, I'm just wondering if the noise distribution can work as a substitute for a different cost function specification. That maybe for certain noise distributions, we will also see encouragement effect, which emerges not because we specify costs differently, but because the noise distribution is such.
Yes, so the noise distribution may affect the shape of this function psi of tau. Wait, I'm writing with the mouse and this is not good. So this function psi of tau sorry, yes. So yes, you're right. That the noise distribution may determine whether you have encouragement or discouragement effect, totally.
So because I'm thinking again about the possible empirical tests of your model. And in terms of empirics, it can be hard to distinguish these two effects, the effect of the noise distribution and the effect of the cost specification. Because usually empirically what you want to identify is the cost distribution or maybe the parameters of the noise distribution. And if you can find qualitatively that these effects can be separated somehow, it would be nice to see this. Because then basically you would help empirical people to test your theory in the future.
I see. Yeah, that's a very good point. Yes, but yes, thank you. Yes.
All right.
And also one quick question, because when I look at the specific, like even when I just think about this possible discouragement, encouragement effects, and going back to motivational examples you gave, if we extend your model slightly, and if we introduce a productive effort in the sense that effort can increase the price you get, it should also mitigate the discouragement effect. I would expect it to mitigate the discouragement effect, because basically once we exert effort, we produce some kind, we increase the price we get. It's like effort depending prices.
Well, it depends with what you compare, of course, because here you don't just make, I don't know, if you make them just one type stronger, of course, then sort of automatically you'll have higher price for him and maybe total effort will go up. But you also have to make the weaker type weaker, and it will decrease the value of the price for the weaker player. And hence, again, the total effect is ambiguous.
No, like if the price depends on the effort of both players.
Yes.
So,
We don't know,
principle,
because
sure.
we don't compare the case of prices depending and not depending on the efforts. You need to, okay, we're in the case of prices depending on the efforts. And well, actually, you can think about our general formulation that already incorporates this case, right? So there is, because we really work with this function f.
Then it's very nice that you can generalize it, and
So
maybe it's
you can put effort here.
Yeah.
Yes. Yeah.
Yeah.
You
So
can put effort
it's
here.
just probably one way to make your result even stronger. So if you say that it also applies to the case of effort depending prices, it makes it even stronger, because you characterize a bigger class of contest games, like R&D races usually have this feature because prices depend on effort there. And then you can say that your result applies in both environments, with where prices do not depend on effort and where they do depend on effort. So it's even like you have even more than you presented.
Right. Okay.
So thank you very much. That's all from me.
Okay.
Very
Thank
good.
you very much.
Okay, please, anyone else?
I have a question that it might go beyond the model, but so I'm thinking okay, I play chess, and well, before I was playing more regularly, and in some cases I was playing with some friends, and for example, if I knew that the person I was playing with was like a very weak player, of course I wouldn't put like such a big effort. And of course, we're also talking about a context in which the price, let's say, is reputation, but it's not like a big monetary price. However, like if I would play this person several times, then like usually like the other person starts improving, and there is a point in which like if my opponent is like slightly weaker than me but has not defeated me, then I might put even a bigger effort compared to someone that is equal in strength to me, and that if, let's say, sometimes I lose to that person, it's okay. If I lose one more time, I don't care too much. But if I have not been beaten before, then I would probably like put even more effort. But in this context in which like the, let's say, the objective price is not big, but it's more about reputation, I don't know if like, I mean, I'm trying to say that, is it possible that like in some cases, like a bit of heterogeneity might increase effort, but if it's too much, then so it's like not linear, let's say, the connection between heterogeneity in types and effort?
Well, I guess so. I would think that this is a model where you have loss aversion, right? Is that if you lose to a player who is worse than you, it's kind of, you feel very bad, right? So, and so you put really high effort. So imagine, I don't know, Rafa Nadal, I guess if he doesn't win, it's super bad for him. If I manage to win at least something there, I would be super happy, right? Because we have different reference points, and hence we have, and if we have loss aversion, that yes, you might have that a bit of heterogeneity kind of may, I don't know, go along the lines you suggest. But I think you need for that some sort of non-very standard utility function, I would imagine.
Okay, thanks.
All right. Well, I'd like to ask a couple of questions, if I may. The first one would be, would you like to think about an inverse problem? That is, would you like to try to describe utility functions or effort functions or whatnot that would generate this heterogeneity effect that you're trying to capture? You know what I mean? Assume that the heterogeneity effect is there, and because you showed that it's not always there for different types of specifications, is it possible to describe the set of specifications, ideally in the most general form, but if not, then maybe from some pre-specified family that would generate this effect? So in that case, you will be able to mock. You showed us that there are a couple of situations. In one case, you do observe the heterogeneity effect, and the other you do not. But I would be interested to ask another question, and that is, what specifications produce the heterogeneity effect? And I think it's possible to do, at least in the simple case of two players. I would suggest you think about this. Possible to.
Okay, yes.
The second question would be, yeah, well, and I would like to second Anastasia. She mentioned noise. So if heterogeneity is a parameter in the distribution function, and if there is some noise, it'd be interesting, of course, to see, because you are stronger than me, right? Okay, I'm afraid that's the case, but let's make an assumption, right? But there might be some noise, and in that case, following on what Bernardo said, I might still be tempted to rely on some luck that I might have, and if I win over you, that in fact makes me to supply more effort. But that's just an aside. And the third, the most interesting one, I guess, is there any way to generalize it? You mentioned that there are ways to generalize it on the case of several players, not just two. Anything you can say about several players? Thanks.
Yeah, so several players. So we think currently that the answer is very simple. It's no and yes. So for absolute types, it all goes through, because I mean you have the generalized averages defined for any number of players. There is maybe some extra properties that you require, but there is really no sort of fundamental difference in anything what we do when you have more than two players, when you have absolute types. For relative types, there is sort of a conceptual problem, is relative to what, right? So when you have two types, it's kind of the two types relative to each other. But once you have more than two types, more than two players, then I think conceptually it's not clear kind of how to generalize it. So it's not, to me currently, it looks not like a sort of technical issue, but more like a conceptual issue.
Well, conceptually, greater heterogeneity is greater inequality, so I can use some kind of majorization approaches. You know what I mean? Yeah. It's sure convexity, or I'm not sure if you know what it is, but
yeah, yes.
Of course you do, right? But anyway, just technical matter. Ideally, I think it would be most interesting if you make your results as cardinal as possible, without actually making any references to ordinality. In other words, one side goes stronger and the other side goes weaker. And you ask under what specifications in this case you do observe this heterogeneity effect. That might be quite interesting.
Sorry, you're saying that we saw this is actually the strong part, because you don't really make assumptions on cardinal things. I mean,
oh yeah, I'm sure it is. Yes, right, true. I agree with that.
Okay.
But never mind. Okay, well, let's see if there are any other comments or questions. And
can I add one quick comment?
Please.
So
yeah,
basically, to support both Bernardo and Leonid, and it also goes back to possible empirical stories which you could use to motivate your new theory. because I think every time you try to sell a new theory, which was not done before, it's important to motivate it as well. So actually what we see in reality is often a non-monotonic effect of heterogeneity. Because, for instance, the paper of Jennifer Brown, Quitters Never Win, about Tiger Woods, which is pretty famous, it's like 2011, she finds a non-monotonic effect of heterogeneity. So basically she finds that heterogeneity hurts the aggregate effort and individual effort when heterogeneity is extremely strong. But it almost does not bind when heterogeneity is weak. So it would be interesting, first of all, to, and usually what people do, they just cite this positive, like negative effect of heterogeneity, and they forget about the absence of effect when heterogeneity is weak. Basically, what you aim to explain can be also viewed as a way to justify this empirical results to some extent. So you can use it as a way to motivate why discouragement effect, we don't see it all the time in the reality. And also maybe to think what could give you possible non-monotonic effect of heterogeneity, because in your story, it's either discouragement or encouragement. You don't have intervals like here it's encouragement, here it's discouragement, here it's no effect.
This we can, so in the paper, there is an example for non-monotonic effect. So this we can generate.
So then well, maybe it would be nice in terms of also selling your results to emphasize this as well. And mention probably that it can indeed explain some empirical regularities we see. And then it makes your story, like at least for me, much easier to buy, because it explains some empirical facts and it helps people to understand where to go with this. That indeed, discouragement effect is not what we always see. And you explain why, because probably in some, at least some groups of contestants, they have a different cost structure.
Okay, good point, I think. Mikhail, a quick question. Did you ever think about doing something not in the framework of contests, but in the framework of teams? To what extent heterogeneity in teams suppresses or increases efforts? Because that would have some links to the literature on the value of diversity. And also, I just recall that, remember Ina Zaitseva, my grad student, she defended her dissertation on the success of soccer teams. And I recall that there is some literature in sport economics on how diversity of players in a soccer team difference in strengths. You have several stars and you have some second tiers, so there is some empirical literature. But this is not about contests, of course. This is why I ask you.
Oh, it's like group contest, right?
Yeah, well, not, yeah, you can call it this way. Oh yeah, good, yeah, group contest. But even without any contest framework, just team performs and people have some stakes in the team success. So how heterogeneity affects success of teams and effort application, that might be another interesting angle.
Yeah, we didn't think about this.
That might be a new development, and that's something that I guess Anastasia also implicitly suggested. Okay, good. I think it's been useful discussion. Let's see if there is anyone else who would like to participate. If not, then let us wish Mikhail and Dmitry every luck in completing this paper and producing much more of the same sort. And hopefully we'll see him and many others soon in Moscow again. And Bernardo, what's next, please? Remind us what's coming up.
So next week we have Jonathan Chapman from New York University, Abu Dhabi, and he will be presenting extension of the franchise and government expenditure on public goods, evidence from 19th century England.
Excellent.
And you can find the announcement in the chat if you want to have more information, but basically next Thursday in same place, same time. And well, I would like to thank Mikhail for participating and for presenting your paper, and best of luck in getting it done, and hopefully like comments here were useful for it.
Thank you very much. Thank you very much, Bernardo, Leonid, for inviting me. Elena, I think Podkozin was also involved. Thank you very much.
Yeah, she suggested me to contact.
Okay. All right. Well, good evening, everyone. Be safe and
Thank
each
you.
other in a week. Okay.
Yeah.
Thanks very much.
Take care.
Take care.
Bye.
Bye.
Bye.